So let's imagine that you just did your basic balances and dimensionless number analysis, and you figure out that scaling issues cannot be fully avoided when moving your process from lab scale to industrial scale. How can we determine their impact? After all, economies of scale dictate that bigger is better, but scaling effects, often arising from incomplete mixing or localized feeding and mass transfer, may become more serious at larger scales. So how do we determine where the optimum lies, and how this is influenced by geometry, by operating conditions, and by our microbial strain? For that, we first need to quantify what kind of local variations exist in our reactor, also called heterogeneity or gradients. Next, we need to know how microbes react to these variations. After all, there may be heterogeneity, but there's no scaling issue if the microbes are insensitive to it. To study a process in detail, we can resort to computational fluid dynamics, or CFD. CFD is all about balancing, and rather than solving macro balances over the entire reactor, we solve micro balances. We split the reactor in many small volumes called grid cells or a mesh, and in each of these volumes, we solve the balances. With this, we gain insight in how certain quantities are distributed within the system. Classical applications in bioreactors are, for example, the analysis of hydrodynamic stresses, mixing, and gas and nutrient distribution. Dividing a domain into many small grid cells to solve a set of equations is called a discrete or numerical solution procedure. For fluid flow, this is not straightforward. You need to solve several balances which are coupled to each other. But doing so allows you to compute local variations. An important factor in these balances is, of course, how things flow between these grid cells which we set up. In other words, we need to compute local velocities. This is also done using a balance, the balance of momentum. You may recall that momentum is mass times velocity, and this balance is also called the Navier-Stokes equation. You see it here on the screen. This is actually a very complex set of equations, which keeps occupying the minds of many mathematicians. It cannot be solved directly, but with a numerical approach and the appropriate processing steps, we can find an approximate solution. Well, our aim of today is not to dive deep into these mathematics. We will leave the full details to a dedicated CFD course and to full-time CFD engineers. But what matters for now is that we can compute these local velocities and that the math is covered by available CFD software packages. And what we want to provide you with is the basic grasp of how CFD works so that you, as a bioprocess designer, can talk with CFD engineers and interpret the results. So let's have a look at the 5 typical steps of solving a CFD problem. Step 1 is drawing the geometry. This should include all the details that matter for the large-scale flow field, such as the baffles, the impellers, and the cooling coils. But small details such as ladders and probes and manholes, those can be left out. These have a negligible influence on the flow field, and the smaller the details, the higher the resolution that is required, and the slower the calculation will be. Now, step 2 is the discretization step. It is important to realize that there's not one single CFD approach. There are different methods which perform this step in different ways. The majority of methods, however, discretize the geometric domain, the aforementioned segmentation of the volume into grid cells. There are methods that do not require volume segmentation and rely on other forms of discretization, but these are outside of our current scope. When the domain is divided into grid cells, we have to make decisions on the resolution that we want to apply. A certain resolution is required to solve the most relevant flow features. And a higher resolution to a degree means a higher accuracy. However, a higher resolution also means more equations to solve and hence a higher computational demand. If the mesh resolution is too high, you may spend many hours computing without leading to a more accurate solution. It is therefore good CFD practice to do a mesh dependency study. This means solving the problem with different levels of resolution and study if the solution agrees between them. Step 3 is setting up the physics. While the mathematical structure of CFD problems is always the same, the relevant physics may vary. For example, the temperature gradients may be relevant in one case, but not in another, and neglecting non-influential physics makes the problem easier to run. In addition, many different models may exist for a certain physical phenomenon. This is because many physical phenomena occur on length scales that are much smaller than the size of the reactor. The flow in the reactor is often turbulent, and the turbulent velocity variations occur on scales of less than a millimeter. In aerated processes, the bubbles are also measured in millimeters, and the film through which mass transfer occurs is in micrometers. Resolving these small scales explicitly, while also modeling the whole reactor, requires enormously fine meshes with over trillions of cells, and our computers cannot deal with this for now or in years to come. There is an important interaction though between the large-scale flow and the gradients on large scale and these small-scale phenomena. And to include that interaction, we do need the physical models describing these smaller scales. Sometimes these models are based on physical laws, but often they rely on measured correlations. And that means that these models are typically applicable in a limited range of situations. Hence, several models may exist, each for a different scenario. And one of the major challenges for a CFD engineer is selecting the right models for any given situation. And this is typically where the discussion between CFD engineers and bioprocess engineers is important, because the latter probably has much more insight in which phenomena actually matter. Step 4 is setting the boundary conditions. The balance equations are the same in each volume, but at the boundaries things are often added or removed. Heat may be removed through the wall, an inlet may add mass, reactants, potentially also heat, and through the velocity of inflow, momentum. And an outlet removes all of these. An impeller transfers momentum into the system, setting things in motion. And without setting these boundary conditions, a stirred tank would simply be a still tank, and for that we don't need CFD. And then finally, step 5 is solving. Again, this is mathematically involved due to the problem's size. Millions of balances often, but it's all happening inside the software. What matters for us is that the solution will not be exact, but approximate. And as a user, you need to decide what is accurate enough. We call this the convergence of the solution. The solution needs to home in on the exact solution. But what is close enough, that's up to you. The more accurate, the more time it takes to solve, and at some point you may not be able to close in any further. In principle, these are the things you need to set up a CFD problem. With proper software, it's literally a matter of clicking the right buttons. But the challenge is in selecting the right physical models, finding the right trade-off in accuracy and computation time, and interpreting the results. That last aspect, in the scale-down context, we will consider next time. But before we do so, let's first very briefly step into validation, verification, and errors. Because of all the modeling choices, verification, the question, is our model implemented well and is it appropriate for a standard problem, is important. And this means comparing simulation data with experimental data collected by yourself or from literature. Consider the following. Has the approach been used in similar problems to the one I'm facing? And were the results sufficiently good to compared to experimental data? Is good quality experimental data even available? This is essentially a scaling problem because data on an industrial scale is rarely available. So this relies on lab scale and pilot scale data. Plus, of course, checking that you're in the right regime with the tools that you're familiar with. Validation, checking if the results are true for the industrial scale geometry that you are considering, is even more difficult. Because for an industrial case, you may have some global data on gas holdup, oxygen transfer rate, maybe mixing time, but that's about it. And this means you still need to be very careful in interpreting large-scale CFD. Are the results logical, and do they match with what we can observe? If so, it's a powerful tool. Otherwise, it can be a pitfall. Now, as a concluding remark, I want to reiterate that there are many different CFD methods. The approach that's most commonly used, and that we used here for illustration, is called the finite volume method. Recently, there has been an interest in alternative methods, in particular the Lattice-Boltzmann approach, which uses a different means of discretization of the domain and a different set of equations to resolve the fluid flow. And if you plan to dive deeper into bioreactor CFD, it's certainly worthwhile to consider different approaches and see which one is most suitable to address your particular questions.